Hello, and thank you for joining us this morning for the third in our Circuit Breaker webinar series. My name is Jeff Ward. I'm the Solution Director at Doble Engineering Company. This series has offered webinars on important circuit breaker topics, and today's webinar is the final one in this series. And they're all leading up to the 2022 Circuit Breaker Seminar to be held September 26th through the 29th of this year in Pittsburgh, Pennsylvania. Our seminar our seminar format today includes a 50-minute presentation, followed by 10 minutes of questions and answers. To ask a question, use the question tool on the right-hand side of the GoToWebinar panel as indicated on this slide. Our presenter this morning is Billy Lau, General Manager of Dielectric Company Incorporated and Dielectric Direct. He'll be speaking on SF6. Billy has more than 25 years of electrical substation equipment and field experience. He's currently responsible for Dielectric's North American operations for sales and delivery of SF6 gas handling, analyzer, and test equipment, and the SF6 field service organization known as Dielectric Direct. Now I'll hand it over to Billy.
Thank you very much. I appreciate the opportunity to be here. I'm going to make sure I get my presentation up. Morning, everybody. Thank you very much. Thank you, Jeff, and thank you, Doble, for allowing us to be part of this webinar series. We're very excited to be part of anything with Doble when it comes to discussions regarding SF6 and alternatives. I'm going to concentrate on, like I mentioned, SF6. Talk a little bit about our history, statistics, SF6 as a dielectric, its effect on climate change, very important, gas handling, also very important, safety awareness, and then emission reductions and what we can do to meet our mission of zero emissions and definitely reducing all emissions to for greenhouse gases. So a little bit about history. So I love this slide because it kind of represents a number of things that happened throughout our industry. Obviously, with the invention and the patent of Thomas Edison's circuit breaker, at that point SF6 wasn't even discovered yet. It wasn't until 1901 when SF6 was discovered by two chemists, Henry and Paul Lebeu, Henry Masson. But SF6 really did not come into play into breakers or GIE until much later. By like 1938, AEG first kind of put out a patent where SF6 was being used as an actual arc quencher. Before that, it was vacuum interruption, obviously air and oil blast circuit breakers. So really interesting. But even still, it had a kind of a slow start. 1954, another application patent for SF6 came out, again using arc quenching technology, but still air blast breakers, oil breakers were still very prominent in high voltage and medium voltage applications. It really wasn't until about 1980s, 1990s, and maybe even some in the 70s where SF6 did become more prominent. You started seeing replacement of air blast and oil breakers with SF6 because of the technology. And now we're moving towards other alternative solutions with SF6 due to the emission reduction plans that are being put out for globally. The history of breakers and GIE. This is a very unique circuit breaker. It was designed by an engineer out of Boston Eliminating Company back in 1897. You can see it's kind of a handle, a manual operated oil circuit breaker. Really neat. Couple pictures of some air blasts. This is very unique breakers. Obviously, you saw them in very high voltage applications, and even to today, you'll still hear or see air blast breakers in like ultra high voltage, like 765 kV or 800 kV, depending on where you're at. and also still in applications at nuclear power plants because of the high breaking current. Really very great medium for interrupting high voltage, though very loud and obviously very costly to operate or to maintain. This is a great piece of history here. This is a breaker, an oil circuit breaker put out by GE back in like 1935. It was a breaker installed to protect the line between Boulder and the city of Los Angeles. 2.5 million kVA at 287 kVA impulse oil circuit breaker. What made this breaker special was that its speed. You know, it was able to basically break or operate under a 60 cycle timing. So really interesting, unique in its time. But you can see the size of it on the picture on the right here. If you see my mouse, that's the individual working on it. You see the size of that breaker is pretty big. And again, you can find more information with the National Museum of American History at the Smithsonian Institute. As I mentioned, SF6 really was not in play until 1901 when it was discovered by Henry Moissan and Paul LeBeau. They obviously were studying fluorine chemistry, and it allowed them, they needed some sort of medium to isolate when they were breaking apart different fluorines using electrolysis. And as a result, SF6 was found, again, man-made by him. He did receive the Nobel Prize in chemistry, but unfortunately, Henry Moissan passed away soon after that. Paul LeBeau went on to design improvements with gas masks, the French gas mask during World War I, which was very important. So obviously, as I mentioned, man-made. You know, it's colorless, odorless, inert. Does not react easily with other substances, which is really important, makes it very important for what it does. Non-flammable, non-toxic, non-poisonous in its pure form. It's got unmatched dielectric strength. It's got great arc quenching capabilities, great thermal stability, in other words, heat trapping, and reassociation. In other words, all these characteristics and components is what makes SF6 such a great material for GIE. It can continue to isolate or insulate. It obviously arc quenches and then regenerates itself without any real need under normal operating conditions of replacing the gas. Times heavier than air, which is really important because of its density. It basically will begin to liquefy at 250 psi at 68 degrees Fahrenheit. And obviously in GIE, we're maintaining a lower pressure than that, so it works in vapor form. Because of its density, it displaces oxygen. So that is something very important. And the OSHA PAL, or the exposure limit, is set at 1,000 ppm V as a result. Unmatched dielectric strength, which means it's 2.5 times better than air as dielectric. It's 100 times better than air when it comes to arc quenching. And basically, it requires high heat to break down the gas. So that's basically what would break it down, if anything, continuous high heat, like a fault, continuous arc or something to that effect. But when that arc is removed, or that heat, that high heat is eliminated, it regenerates and basically is ready to go and do its job all over again. Let's talk a little bit about it as a dielectric. In case you didn't know, high voltage, low voltage. SF6 obviously is found in high voltage and medium voltage equipment, not so much low voltage. But as you see on the graph on the left side of the screen, SF6, as the kVA rises and the gap increases, SF6 is an excellent dielectric. Even at 1 bar, which is 14.5 psi, SF6 is still a much better dielectric as the kVA or the voltage goes up. Even at bar, it is much better than air as an insulator. You can also see on the other side of the slide, at different percentage, different mixes, its ability to not break down as easily under high voltage as pressure increases. So a little bit more on its capabilities as a dielectric. Obviously, SF6 being what it is, doesn't take as big as a footprint as if you would have to use oil or air. If you remember from the slides earlier, the one large oil circuit breaker that was pictured from the Smithsonian, that's a very large piece of equipment at over 200 kV. Again, if there was an SF6 breaker in place, which most likely now is, it's not going to be as big. It doesn't take as high as a footprint. If it was air, like the air circuit breakers I showed you, also taking up a high footprint, but then it requires air compressors. You need to maintain that air quality and that air pressure very high. Oil, of course, also requires more attention than SF6. A lot of these parts are less common now. Takes a very large footprint and has been known to produce hydrogen explosive mixtures when air is introduced under arcing conditions. And not as easy to dispose of, although there are different minerals and everything else, but still, you know, a difficult medium to deal with. Under vacuum, vacuum's been around for a long time, as you saw from my first graph of history. However, again, SF6, as the gap spacing increases and the voltage increases, SF6 maintains a very strong dielectric strength. If you were to use vacuum, you would need, again, much larger footprint. You'd have no ability to watch that vacuum if there's loss of vacuum. So there's some challenges there as well. So keep that in mind. Where does SF6 lie inside of high voltage or a GIE piece of equipment? So as you see in the yellow, this is where basically SF6 would do its job. The GIE on the left is a large sample of a large GIE chamber. So throughout its chamber, allowing for a small footprint. So basically, you would the space that a 550 kV dead tank out in an air insulated substation would be much larger than what a bay in a gas insulated building would be. But yet a lot of SF6, right? There'd be a high volume of it throughout its chambers. On a live circuit breaker, for example, the one in the middle, not only would it be found in the interrupting chamber up at the top, but also in the supporting column and even in some of the transmission components, depending on its design. On a dead tank, like the one on the far right, throughout its whole tank, throughout the volume of the bushings as well, and in some cases, in this case, you see that the CTs are outside the SF6 compartment. But in some cases, you'll find the CTs inside the SF6 compartment, especially when it comes to GIE or gas insulated substations. Its effects on climate change. So in 1997, the Kyoto Protocol, called the Global Warming Treaty, was listed SF6 as one of the 6 greenhouse gases that should be normally controlled by reducing or eliminating its use. In other words, it was found that it was one of the most potent greenhouse gases, with over 100 period of SF6 at 22,800 times more effective at trapping infrared radiation than the equivalent of carbon dioxide. So in other words, 1 pound of CO2 is how we measure our greenhouse gases. So 1 pound of SF6 would be 22,800 pounds of CO2 collectively to that effect. And also, it's also very stable, as I mentioned before, because of how SF6 gas works. It would accumulate in the atmosphere, and essentially in an undegraded state. So it's got a lifetime of over 3,200 years, meaning that even SF6 that possibly Henry Moissan himself created may still be in our atmosphere, if you can kind of put it to that amount. So any small amount of SF6 obviously has a major impact on climate change. Be it known that the United States did not sign on to the Kyoto Protocol, but they did adopt a lot of the principles that were outlined in the protocol to reduce emissions as a major developed country. The Paris Accord, or the Paris Agreement, also known as Paris Climate Accords, International Treaty on Climate Change, was adopted by almost 200 countries in December of 2015 and put into force in November of 2016. So it covered a number of things. obviously change mitigation, adaptation, and finance. And how does that work? So the protocol essentially, or the agreement essentially, was set out a limit to countries that were part of the agreement to pursue efforts to limit global temperatures to rise from 1.5 degrees Celsius and keep them well below the 2 degrees Celsius. So this is above pre-industrial times. We want to limit greenhouse gas emissions from human activity to the same levels that trees, soil, and oceans can absorb naturally. And each country had to set its own emission reduction targets, reviewed every 5 years to raise these powerful countries or rich countries or major countries would help poor nations or underdeveloped nations with funding to help them in climate change to essentially switch over to renewable energy. As you can see from the graph, we're not doing very well. So we're kind of missing our target a little bit. The path that we wanted, as you see, is the one that's right here, if you see my mouse. So that's the path we wanted to be in, but unfortunately we're continuing to rise on and global greenhouse emissions. So remember that SF6 is not ozone depleting. It's not depleting the ozone. What it is it's trapping the UV rays. So this illustration essentially shows as the sun rays come in, for the most part, they can be reflected back to space or absorbed into the atmosphere. But what is happening more when there is greenhouse gas effect is this right here. There's a radiation back to the surface. It's trapping heat, trapping the UV rays on Earth. So again, it's not an ozone depleting gas. Effects on climate change. Because SF6 does not naturally occur in abundance, there are some traces of it found that it has, but obviously not to the level of what is needed. It's manufactured via 4 major processes. Very important to note that during this manufacturing process, byproducts such as SF4, SF2, S2F2, S2F10 are also produced. Other impurities like moisture, CO2, air is also introduced to the gas, and all this needs to be scrubbed out. So the process works like you see here throughout this illustration. Through a process of electrolytic process, we produce the fluorine gas, much like Henry Moissan did in his work. We introduce the fluorine and the sulfur to produce SF6 gas. And at this point, we're creating a number of those byproducts as a result. And those byproducts are released as part of the scrubbing process, where we use activated charcoal or aluminum oxide, molecule sieve desiccant, and particle filters to scrub out those byproducts. And then a cryogenic and a high pressure separation process, much like what we do in reconditioning, is done. And at that point, we scrub out all those bad contaminants. We also reduce the other air and other CO2 contaminants that are in the SF6 to produce pure SF6, which is then consolidated, put in the tanks, and then introduced into the supply chain. And again, that last piece, that separation process, is also the process for reconditioning of SF6 gas, which I'll touch on a little bit later. SF6 produced can create between 3 to 8 pounds of emissions. So think about that, 3 times 22,800 or 8 times 22,800 of emissions. So quite a bit of an impact on climate change when virgin SF6 gas is produced. That equivalent 1 pound of SF6 is equal to 10.3 tons of CO2. So in other words, if we drove 2.2 cars, an average size vehicle, for a year, we would create that much emission. Or driving, again, an average size vehicle, 24,786 miles, we would create that much of an emission. So keep that in mind. That's the equivalent of that 1 pound of loss of SF6. Gas handling. So Abraham Maslow, he wrote a book, and if all you have is a hammer, everything looks like a nail. So what we're saying here is have the right tool for the job. Planning is extremely important when the gas handling. Very important. You got to understand the scope of work. You got to prepare for that scope by acquiring the tools and equipment to accomplish the scope safely and to meet the goal of zero emissions. So plan, know, prepare, acquire, and then you can execute. So for example, having the right size equipment for the GIE volume. The smaller the breaker, not as large a recovery system or tools or equipment needed. The larger the GIE, the larger the recovery system. And I'll explain that further, but basically think about it this way. If you need to recover 100% of the gas, you're going to need a tool that can accomplish that efficiently, promptly, and safely. Know the condition of the gas you'll be handling. This is really important in preparing yourself. You want to know that you're dealing with clean gas or you're dealing with contaminated gas. So testing, field testing of the gas before you handle that gas, before you connect to it, is really important. What kind of pre-filters do I need? Do I have a low purity, which means I may have air or other vapor contaminants in there, which means I need more storage space. So really important. Verifying the temperature corrected pressure. Very important for a couple of things. One, it's going to tell you if this thing is leaking. Two, is it overfilled? Is it underfilled? Do I need to prepare myself to recover that final amount with air contamination? So again, knowing what the correct temperature corrected pressure is and the condition of the gas is part of your planning and part of preparing for the recovery. Start from 0 or less than 1 torr. What do I mean here? I mean that your equipment, your tools, should be properly prepared in order to accomplish the job. If you have any SF6 or residual SF6 from either a prior job, prior handling, you're liable to cross-contaminate. You're also going to throw off any accounting that you're going to be able to do. So if unless you know that you have X amount of gas in your cylinders already, you already have a determined weight on it, you really should start with empty, under vacuum cylinders. If you're going to reuse that gas, you want those cylinders to be clean and free of any contamination. Same with your hoses, your pre-filter. If you're using a pre-filter like you see here between the two hoses on the left side of the screen, that pre-filter needs to also be clean, especially if you're starting from scratch. You don't want pre-filters that have been used for a year or more than a year seeing contamination. You're just going to cross-contaminate. You're going to pass that contamination onto the gas, and the gas will not test well after recovery. You're also going to introduce contaminants into your recovery system, and thus eliminating the good service life of it, or thus reducing the service life of it. Also, your hoses, any of the accessories that you'll be using. Make sure that your cylinders are under or within the certification date. This is really important, especially for transportation reasons. Using cylinders that are out of cert is not only a DOT concern, but it's a safety concern. Cylinders that fail, valves could be leaking. There are cylinders that do have contamination on them, etc. So having cylinders within certification is very important. Having a flow meter or cylinder scale that are calibrated, and also, by the way, that if you're using a mass flow meter, that it doesn't have gas from a prior recovery job or anything like that, so we can avoid contamination. You want to start with that mass flow meter at 0. Your scale, you want to be sure that it's calibrated and it's designed to handle cylinders. But we don't want to see a scale that you buy at Bed Bath & Beyond or Walmart or some other store that is not going to be able to handle what the industriousness of a cylinder is. It's a piece of metal. You're able to come down on the scale. You're not going to have good readings if you're using a non-industrial scale that's made for cylinders. So in gas recovery, very simple. We have our GIE on the far left. We got our recovery system, which is made of a number of things, including a suction pump, sometimes known as a vacuum compressor, a compressor, onboard filters, particle filter and a dryer filter, and then our storage, which could be a tank or a cylinder or a number of cylinders. Our vacuum pump does not come to play at this point because we are doing either recovery or fill, depending on what you're doing. And if you follow the different lines, you see how that works. or if it's a GIE that's been in service for some time, highly, highly recommend that you use a pre-filter in place. This is really important. Again, you're putting this gas or you're introducing this vapor that may have contamination through a number of components, including the vacuum pump, including the compressor, including the filters and your hoses and accessories. So having that pre-filter in place is going to make sure that you're not going to cross-contaminate, and you're going to end up with a product, a material at the end that you'll be able to reuse. So you'll be able to recover, recycle, and reuse. 3 R's. For vacuum, obviously you don't do that with pressure. Vacuum pump is going to be the only component that generally has oil with it. Obviously oil and SF6 do not do very well together. So the vacuum pump is strictly designed to evacuate air and moisture from a compartment. You would also use it, of course, to evacuate air and moisture from cylinders or a storage tank in this application. So recovery of gas. So in this example, you see if we were to have a GIE at 90 psig and only recover to 0, we would only recover approximately 86% of the gas. 86%. That means that at least 14% may still be in the GIE. This is why we need to be sure that we have the right size of equipment, the right accessories to be able to recover 99.9 to 100% of the gas from that GIE compartment. So it all depends on the size of the GIE too, by the way. So let's say a large GIS station or a large chamber like you see at the top right of the screen there, you may not be able to get down to 1 torr. You may only be able to get down to 5 torr, but that should still help you recover 99.9 to 100% of the gas. Smaller GIE like a line breaker or a live tank breaker, or even a small GIE like a small distribution switch like you see here at the bottom. Those type of units are so small you'll be able to recover down to 1 torr. Again, using the right sized recovery system for this application. Regulations like the EPA, state, etc. They're all, looking at the environment and making sure that we're doing the right thing. There's different states now also looking at what CARB has done. The EPA is also studying what CARB has done. We need to be prepared. I mean, things are changing. The environment is a very large topic right now, as it has been for many years. And we need to understand what we as an industry and as a community of SF6 gas users need to do to reduce emissions and limit the implication of greenhouse gases into the atmosphere. Some state regulations like CARB just recently came out with a new regulation. They just recently released it. They worked very hard and diligently going through it. They turned to working groups and the Joint Utilities Group in California, the SF6 Gas Coalition and SF6 Gas Alternatives Coalition. A lot of resources that they turn to acquire the right information to create this regulation. So really important. MassDEP also very deep into the reporting process, and many states like you see here are looking at these regulations now to see what they need to consider to reduce emissions within their jurisdictions. And investigating SF6 in 1997, right around that Kyoto Protocol time frame. But the mandatory reporting didn't really kick in until 2012. So a couple subparts to it. So subpart DD, which is for electrical transmission and distribution equipment, basically for utilities that report emissions if their nameplate value exceeds 17,820 pounds. All right. So that's excluding hermetically sealed pressure GIE, by the way. And then subpart SS is for electrical equipment manufacturers or OEMs. They must report emissions or related quantities in total annual purchases of SF6 that exceed 23,000 pounds. Additional information on the EPA website. They have numerous amounts of papers, information on their website, and you could even see some greenhouse gas reporting information on the website. Here it is, the greenhouse gas reporting tool. So what this tool does is it allows for stakeholders and the public to essentially log into the EPA website and literally view by state and by utility their reported emissions and gas usage. So really interesting if you're trying to see what reductions are happening. The great thing about it is the EPA does an excellent job of putting this information together, and they have essentially seen a great reduction in emissions since reporting started. So really good. And as reporters are able to reduce their emissions over time, they no longer have to report. It becomes more of a voluntary reporting requirement. Regulation that came out in January of 2022, the new regulation is released for 2021 reporting. And I'm just going to kind of go through a couple of things that changed in the regulation or was updated. So they updated the definitions and the acronyms. They eliminated the annual allowable emissions. So in the past, there was a graph where you saw we went from 10% to 5% to 2% to 1% over time, 1% being by 2020, 2021. Well, that emission rate no longer exists under regulation. There's a SF6 phase out schedule, and that's per the equipment rating. There's an update to the emergency event exemption, annual emissions limit calculation, exceptions and inclusions for covered gas. The reason this part changes because they're not only considering SF6, they're considering SF6 gas alternatives. And also it allows for an early action credit of an SF6 user who implements alternatives into their system. There's an update for inventory and insulated gas procedures. Calculating the annual emissions has changed. Update to the reporting requirements, update to the record keeping, and of course, mentioning that there's a phase out as SF6. There's also an exemption and failure notification update on the new reporting or the new regulation. They also included a nameplate capacity adjustment, which has been very controversial over many years because we know that nameplates aren't exactly correct all the time. We could be, have more gas in a GIE or less gas in a GIE, and that could obviously impact reporting. So the regulation clarifies how that adjustment should occur. And then there's an update to the enforcement. So what are some of the options to help reduce emissions? Well, obviously, one of the best is training programs for field teams who handle SF6. Getting them the teams up to date on what the impact is when they don't handle SF6 correctly is important to help them realize that. I just recently did some training where a number of technicians who do handle SF6 in the field didn't really realize that environmental impact. And they were enlightened, but to know that if they do it right, they contribute to emission reduction. So that's really good. But also showing them and training them and keeping them trained on how to properly handle SF6 in the field without needing to vent, without needing to purge to the atmosphere. Many good handling practices. I'll add this. Is it always easy? Is it always the most efficient? Obviously not. When you're creating processes that help improve situations such as emission reduction, obviously more time, more efforts involved, but it's for the right reason. Using certified gas handling specialists. Maybe you don't have a big enough team to go out there and do your gas handling. So bringing in teams or organizations that are certified in gas handling and understand the scope of accountability, emission-free recovery, no emissions to the atmosphere while handling is very important. Maintaining your GIE to eliminate SF6 gas leaks quickly and safely. Not having that cylinder strapped to the frame of the GIE with a little positive pressure, getting rid of that concept needs to come into play, and replacing those leaking breakers right away. Implementation of the 3 R's program: recovery, recycle, reuse. Remember what I mentioned, if you're constantly relying on virgin SF6, you're just contributing globally to the greenhouse gas emissions. So we have plenty of SF6 here in North America. We have plenty of SF6 in Europe. We have plenty of SF6 in our industry. Not saying that virgin SF6 isn't needed. There are applications where that virgin SF6 is definitely the most important thing to use or really highly needed. But there are programs that you can put in play that will limit the purchases of SF6 and concentrating on either using reconditioned SF6, which I'll show you an example of in the next slide, or a 3 R's program within your organization where you recover, recycle, reuse. And again, there's training programs behind that. Using self-sealing fittings, appropriately sized and maintained recovery equipment. Again, this helps in reduction. If you use a piece of equipment that won't recover 100% of the gas, you think you've gotten as far as you can, but it really can't get to that blank off pressure, if you will. You're gonna leave SF6 gas in the GIE. When you open a compartment, you're just creating a spill and you're introducing greenhouse gas into the atmosphere. Utilizing accounting techniques. You need to know what you've handled. How much gas have I recovered? Have I recovered 100% of this gas, or did I leave some in there? Really important to know, and that helps you understand where you stand as an organization. Not only if you're a utility, but also organizations that support utilities. They need to be able to do this and help the utility or the SF6 gas GIE owner have a great understanding of their SF6 inventory. And again, I mentioned replacing leaking SF6 GIE with new or non-SF6 gas alternatives. That's great. So we can, over time, we can reduce our emissions by implementing all these different programs and concepts towards SF6 emission reduction. So again, I mentioned the 3 R's and I mentioned reconditioning. So what's the difference? The 3 R's: recover, you recycle the gas, and you reuse it right away. Great program for you. Cost reduction, if that's a major factor for you financially, but also emission reduction. Remember what I mentioned: 100 pounds of virgin SF6 when produced can create between pounds of emissions. When the same 100 pounds of reconditioned gas is only equal to or less than 0.64 pounds of emissions. And when you implement the 3 R's in the field, you're talking about 0.5 pounds or less of emissions. Major impact on emission reduction. And this information, by the way, you can find it in the 2019 refinement of the IPCC guidelines. They just came out with the 2022, or came out this year with 2022, and it doesn't create any changes to what was mentioned in 2019, but it's a lot of reading. I believe it's over 250 something pages, but nonetheless, the 2019 addressed this really well, and I think that's an important thing to consider when using or relying on virgin SF6. Reconditioned and recycled SF6 gas, the 3 R's, by testing and seeing that the gas meets the targets of what you need, the specifications, you could easily reuse SF6 gas in the field. While there's no better electrical insulator than SF6 for medium and high voltage circuit breakers, obviously this gas presents its challenges being a greenhouse gas. It's a potent greenhouse gas with important safety considerations. And it's really important and really imperative to follow the best practices for SF6 to not only ensure the personnel safety, but to prevent emissions into the atmosphere. So very important. All these different techniques I mentioned, I know we went through them pretty quickly, pretty briefly, but we as SF6 stakeholders have a responsibility to reduce our emissions in the field globally. I did concentrate a lot on North America and the United States emission reduction and regulations, but the European sector or the European region is also looking at it. In fact, they're also doing SF6 gas usage elimination programs, and they're looking to eliminate the introduction of new SF6 projects into the grid. So this is a global thing. It's not just here in the United States or here in North America. It is global. So remember, don't be a gas hole. Don't emit SF6 greenhouse gas into the atmosphere.
All right, thank you, Billy. We're going to move on to question and answer. I can't tell right now if I'm showing the screen. Yes, okay, looks like it's up. We do have one question, and we have plenty of time to take some more. So those of you who are attending, please, if you have questions, I can see some more coming in now into the question box. So we'll get to those in just a second. While you're thinking about those and entering them in, I'm just going to put this slide up for your information. If you're interested in learning more, Dilo will be offering a 4-day training. That's a paid training event on SF6 gas handling and circuit breaker testing fundamentals in cooperation with Doble, July 18th through 21st in Odessa, Florida. And in addition to that, you can learn more by visiting the Dilo Academy at the link here. In the coming weeks, as additional course information and dates are provided. And the other thing we want to make sure you're aware of is that you can join us at the Circuit Breaker Seminar 2022 this September, the 26th to the 29th in Pittsburgh, Pennsylvania. Attendees of this seminar, this webinar, can use the discount code shown to save $100 on registration. So I'm just going to leave that up for a minute, and I'll start with some of these questions. If you're ready, Bill. So the first one is from Nick. Is there an industry guideline, either IEEE or IEC, or recommendation, industry recommendation on the acceptable operating limits for sulfur dioxide and moisture for SF6 breakers? And if there's no industry standard guidance, then is it advised for the equipment owners to use guidance from the SF6 breaker manufacturer?
Well, if I understand, the question is, it's using sulfur dioxide? Is that how it reads?
I think it's acceptable operating limits, probably on levels of SO2 and moisture in the gas.
Oh, thank you. So yes, there are. So the different standards, whether you're looking at IEEE, IEC, SIG, have references to SF6 gas in service. So there are limits. So for example, you could see up to 500 ppmv of SO2 in a breaker in service. Obviously, if you're introducing new SF6 or you've recovered that SF6, you want to scrub all that SO2 out of it, but there are limits. So generally, you'll see everything between 12 ppmv in some standards, and then some OEMs and some others adapted 500 ppmv of acceptable contamination for in service.
Okay. Next question from Enoch. Can a reduction in recycling program be implemented at any facility? And what would that look like?
Yeah, absolutely. What would it look like? It all depends on how far you need to take it. So it would essentially, the program can include training of your own personnel, implementation of the proper tools depending of your applications. If you can't train your own people, if just the scope is too broad, you could turn to organizations which have already programs in place that could support other entities or other organizations. They'll already have, gas handling processes and procedures. They'll already have tools. They'll even have processes in handling contaminated GIE, which requires like, mask programs, like, respirator programs per OSHA, handling of contamination, et cetera. And it changes. So you got to be careful state to state, entity to entity.
All right, thank you. What are the common replacements for SF6?
So we don't really call it a replacement per se, because when the alternative that exists are everything from mixed Novec gases, clean air, vacuum. So they're alternatives. So there's a number of them, and you can look at different applications because the mixtures can right now vary. We're not at a place where we've decided on one specific. We have quite a few options, I should say. So just some examples, again, Novec mixed applications or Novec mixed gases, vacuum, clean air. So.
Yep. Yeah, if you look around a little bit, you'll see the different OEMs, touting their solutions. So there's quite a variety of options. From Jeff, which impurities can be easily removed from SF6 using field processing equipment?
Okay, excellent question. So generally anything, so when we have breakdown of SF6, we have a number of contaminants that can be created. I kind of listed a few of them. So SO2 being the most prominent because it becomes the most stable, but anything behind that. So when you have SO2, you have other ones. So HF, SOF4, S2F4, CO2, which other air impurities. So in the field, you could scrub out the byproducts. So the SO2 and everything below that, the HF, the SOF4, the SO2s, all those type of contaminants, moisture that you can do in the field. Other vapors, more difficult because that requires a high pressure and cryogenic process.
Great. From Luis, can Dilo certify my team on the handling process?
Absolutely. As Jeff had showed, we have a gas handling and circuit breaker testing class coming up here in Odessa, Florida. And depending from where you're at, if you're international, different facilities for Dilo throughout globally have the ability to train and certify.
All right, so you can just follow up with you on that, I'm sure.
Site, send us info on your company and we'll follow up.
Cool. From Dale, is there a proposed target date for the phase out of SF6 gas?
So it's specific to right now, California. And yes, starting 2025, dependent of voltage and rating is when the phase out begins. Remember, very important to understand this, the phase out is for new projects. So if today we plan a project that's going to be installed, commissioned in 2026 of SF6, it's basically an ongoing project starting today. So it doesn't mean that in 2025, because I planned it in 2022, I can't do it. It's new projects starting 2025, and then it progressively changes as the technology also changes. So, we've got example that will be phased out later on, and we're talking about 2035, 2036, something like
that. Okay. From
Sorry, Jeff.
Well, we want to be clear on this. From Nick again, great presentation, Billy.
Thank you.
Expand more on the SF6 self-healing process after an arc is quenched. How long does recombination of SF6 typically take? Would you expect to see values of sulfur dioxide, parts per million byproducts from a high current fault? Let's see, I gotta scroll a little bit to go down after time. Okay, so two different questions there. How fast does SF6 reconstitute itself? And would you expect to see values of sulfur dioxide byproducts from a high current fault go down after time?
Awesome. So great question. So the process of regeneration is, we use the term almost immediately. So as soon as that high level of temperature, that arc is quenched, the SF6 begins to recombine. So just break it down a little bit. So you have the SF6 molecule, the different components, the fluorines break apart as it's creating a resistance across the arc, absorbing all that energy. And that's when it all breaks apart. The minute that arc goes away, all the components of SF6 recombine to an extent. To your point to the second question, yes, you may have some contamination, residual contamination over time at normal conditions, but on a major fault, have I seen reduction of SO2 or reduction of contaminants? Yes and no. So as I mentioned, SO2 is the most stable, right? So being the most stable is just the easiest one. HF, for example, you can measure HF, but I can measure it today and get, let's say, 500 ppmv of HF. I could go back tomorrow and now I'm reading 200, but maybe my SO2 went from 200 to 600. So that's HF continuing to break down and becoming SO2, for example. But we have seen where, other contaminants can, I guess, revitalize themselves or rejoin the SF6 component. I've done where I've captured contaminated SF6 in a cylinder, shipped it across the country, got to where it needed to be, and then there was a mass reduction on contamination for no reason other than the fact that it was a very dry container and it was not exposed to any more heat or any more temperature. So can it happen? Yes, but generally what happens is you have increased component breakdown or contamination because of the fact that there is so much contamination. It's just constantly reattaching, rebuilding itself. And that's when you get a high buildup of SO2 results.
All right, and there's a little overlap between that question and the next one from Marco. Marco asks, can you say something about contaminated SF6 or the situation after flashover, for example, powder, kind of the residue perhaps?
Sure. So obviously that's the solid, right? That what people know as the white powder in GIE could be a combination of a number of things. It could be tungsten, it could be copper, it could be all the different metals and components from the interrupter itself, especially after a major fault, right? Because it's just a lot of heat and you have a lot of stress on all those different components that make up an interrupter. So that powder can be a combination of all those metal components or conducting components that are within the interrupting chamber. But also remember that just because you see powder or just because you don't see powder doesn't mean SO2 or contamination is present. It could be in vapor form as well. And again, this is why we test. We test from vapor, right? So just keep that in mind, that just because you see powder or don't see powder doesn't mean that there isn't contamination. And then, yeah, so the powder has to be handled in a certain way, or rather the contamination needs to be handled a certain way. It's very toxic. It obviously already had a negative effect on the components of an interrupter, but even worse, it can have a negative effect on you from a safety perspective. It could, if you're exposed to it, it can damage your respiratory system. You can have a massive effect on your skin. Some people react differently to contamination on their skin. So you want to make sure you have programs in place to protect personnel dealing with going into GIE that has contamination.
Great, thanks. We got about 5 minutes left, and we still have, or 4 minutes left. We still have a few more questions. This one from Angela, I read it and I'm like, yeah, how come? But I kind of know the answer, but why is SF6 in the atmosphere if it's 5 times heavier than air?
So moisture
dropped out there for a second.
Very reactive. And I start with that because obviously in our atmosphere we have evaporation and so on and so forth. So SF6 will tend to, or rather moisture, because moisture being the reactive molecule that it is, looks for the driest component to wrap itself to. So moisture, this being moisture and this being an SF6 molecule, will wrap itself, and then evaporation can bring it up to the atmosphere. There's winds and wind currents that'll lift SF6 to the atmosphere. So there's just the typical atmospheric rotation of the Earth and everything that'll just rise it to the. If you see a piece of paper is heavier than air, but yet with enough wind, it'll come up and float above the air. Well, imagine the same thing with SF6. So there's many different reasons, but moisture being one of the things.
Yeah, I mean, you have to think about, just think about your average rain cloud. It probably weighs tons with all the water, moisture in it, and yet there it is. But a good question. I looked at it, yeah, how come?
I love that question.
Yeah, from Corey, could you please talk about room monitoring systems, I presume, against hazard situations?
Oh, absolutely. So room monitors, really important safety aspect, especially in gas insulated substations like buildings or where you store SF6. Room monitors can be used in a number of ways. The most important aspect is to be advised of a spill that may occur in a building or an enclosed location. So really, really important. But it can also be used to kind of isolate where a spill is occurring. So depending on where a zone is placed, you can eliminate by literally reading a panel on a room monitor, saying, okay, zone 1 has got 3 ppmv of SF6, but zone 6, wow, that's got like 300 ppmv. So that leak can happen in that area. So it can bring more than just the functionality of advising you of a spill and not to enter due to asphyxiation, but also kind of help you eliminate literally by a little sleuthing there of just reading the different zones of where that leak or where that spill is occurring at.
Okay, we already talked about alternatives, so I'm going to skip over that one. At what SO2 contamination limit do you need to start looking at PPE, like respirators, et cetera, before opening a breaker for maintenance or seal replacements, et cetera?
There's no reason to introduce any contamination to your body, skin, or respiratory system. So we know that if we have greater than 0 ppmv, we're donning on our PPE because it's very likely that while you might be reading some low numbers, as I mentioned earlier, you could have an increased amount occurring, especially once you open the atmosphere. All that moisture, all that reactive of humidity is going to create more contamination.
Great. There's another question from Angela. Good question. Does SF6 get into the soil at all? Do we know?
So there are some studies with the EPA has a term for it, and I apologize, but there are some studies, and actually, if you remember what I said, there are some naturally occurring conditions of SF6, but it's not found heat sinks. It's not found in high levels. You usually find more like nitrogens and CO2s and things like that. But no, I want to say that if you find it, it's usually because of natural occurring reasons, not necessarily because of SF6 gas spills.
Okay. Well, we are at the noon hour here, U.S. Eastern Time. We have to wrap it up. There were a few more questions. If we didn't get to your question today, I think it's fair to say you could send an email to billy@dialo.com, and he will do his best to answer it for you. So again, thank you all very much for your attendance today. And don't forget the training opportunities offered by Dialo and Dialo in combination with Doble, and your discount code for the Circuit Breaker Seminar in Pittsburgh this September. Again, thank you all, and thank you, Billy.
Thank you. Appreciate the opportunity. Take care, everybody.
See you.